So, till the time we are waiting, Porter, can you just tell us a bit about your background, like before joining Matter Labs, what you were doing, that kind of stuff?
Yeah, good question. So yeah, before joining Matter Labs, working on the security team here with Rahul, I was a Solana security auditor. And I spent about 2 years auditing a lot of Solana projects um, and a couple other ecosystems like Sui, Algorand, Near, um, a lot of things that were not Ethereum related. But now I've come home and working on, in my opinion, the best ZK rollup. I guess even before that, I studied math and computer science in college, and I always really liked sort of cryptography, and so I'm very happy to be working on like a cool project where cryptography is like making a big difference for people in the world.
Nice. I think this is the best roll up, in my opinion, not because I'm getting paid. Still, I'd say. And I think there's still some time to start. So, I learned one scandalous fact about Solana just yesterday, that Solana smart contracts or Solana programs, whatever, they are not immutable by default. Like in EVM, you have to deploy a smart contract and then upgrade it using a proxy. But Solana, you can deploy just another contract at the same address and boom, it's upgradable. Is that true?
Yeah, Solana contracts come with a upgrade authority, and you can set it to like the burner address or something, or you can turn it off. But I'd say it's more like they just have a simpler upgrade process. Honestly, it's built in.
Nice. But that also means that if you are using, like doing an external call to another contract, you cannot get it transparent. Thank you, Solana.
Yes. Um, yeah,
Okay.
there definitely some drawbacks. So I'm happy to point out technical flaws of Solana some other time, maybe.
I mean, we should create a comeback video. Did you see the video that they put out yesterday?
No, wait, which one?
ETH mechitis, like some kind of illness that you have if you are a ETH maxi. Like, let me just forward it to you.
Okay, yeah.
Yeah. I mean,
I volunteered to go on some like Solana podcasts to do the like Ethereum L2 versus Solana debate, and then
okay.
I think all of them get scared of actually debating me because I think they're all worried they might lose.
Yeah. I think the video that I saw yesterday, that was the finest piece of propaganda I had seen in a while. Finest piece. Yes.
Nice.
So thank you guys for this short introduction about yourself. We had like some issues with microphones, but I think we are ready to kickstart this session. First of all, like thank you, Rahul and Porter for joining us, accepting this invitation for doing a workshop on ZK one-on-one at New York. We are super honored and happy to have you here, guys. And for anybody who is joining us, they are going to give us like a little bit of introduction, and feel free to go all deep in the tech aspects here, because we have a bunch of tech devs at T-Org, and also like some community members that are joining right now. And for anybody who don't know who both are or Rahul, these guys are from ZKsync, so OGs in the space. Feel free to take the stage and let us know about what you guys are building and a little bit more on ZK.
Okay, sorry. I tried to join from my phone and it messed everything up. Are we ready to begin? Should I share slides?
Yes, please.
Cool.
Yay, let's go.
Rolling. Intro to ZK with me and Rahul. So also please, I guess, chat anytime you want. I'll try and keep up with all the questions, and yeah, ask away. So yes, we already did some of the intros, but yeah, we like math and ZK. We work at Matter Labs, which is the company that's building ZKsync. As we've said, that is the best roll-up in a lot of ways. And the outline for today, well, I guess we'll get back to background ZKsync, but the outline for today is like basic ZK intuition. I have a problem that I like walking through that should help you kind of understand more of like the math side of things, what's going on. And then we'll cover, I call it ZK buzzwords, but it's just like a lot of basic ZK terminology that is confusing when you're a beginner, but once you understand it, you'll be able to like learn a lot more things on your own very quickly. Then we'll get to how ZK rollups work, in particular, how ZKsync works. And we'll wrap up with a little bit in the current state of ZK, and then we should have lots of time for questions. So as I said, please chat anytime and speak up anytime. So yeah, first, I guess, background on ZKsync. ZKsync Era is a layer 2 scaling protocol. Our goal is to scale Ethereum, so make it faster and cheaper for end users. And we want to do all of that while keeping all the values of Ethereum, such as trustlessness, security, resilience, community ownership. And it's really like the ethos and values that like technically we're already like, I think, the best project, but the values and ethos keep driving us to work hard and keep us on the right track. And I think that's why long-term too, we will stay probably the best, at least competing with the best roll-up teams. Cool. Everyone ready to dive in? True.
Yes, we are.
Okay, yeah. So the only math background that I tell people you really need is that different polynomials are mostly different. Oh, I'm a
Your
math
screen
person.
disappeared.
No, it disappeared.
I mean,
Is
I
that-
think it did. Can someone confirm the chats? Oh, okay.
Sorry, does it flicker on and off? That's me like trying to look at chat and then trying to scroll back.
Okay, it's there.
Okay.
Yeah.
So different polynomials are mostly different. Yeah, like I'm happy to go like super into the weeds of math if you guys want to learn all about elliptic curves, but I think that's not something you should focus on at first. You can get most of the intuition just from this. So what I mean here is like on the screen, we have two quadratic equations. Quadratic equations are degree 2, so they can intersect in at most 2 points. Otherwise, they're just the same quadratic everywhere. What this means is if I have, say, like 1,000,000 points and I randomly check whether two quadratic equations are the same across these 1,000,000 points, at like 999,998 of them, these parabolas are going to be different. And only at 2 points will they be the same. And so if I go over like an even bigger range, say like 2 to the 256th or something, then there's pretty much no chance that I accidentally pick the point where they overlap. And I can tell whether different polynomials are different just by randomly checking them at one point. And so as long as the polynomials are somewhat low degree and the field size is really, really big, then we'll be able to tell polynomials apart very fast. And this is really cool, and I'll get to more why it's cool, but that's the only math you need for today. A motivating problem is, so this problem I would say is like not really ZK, but it should help give you the intuition. Let's say you have 1,000,000 data points and you send everything to this person, Eve, who is not trustworthy. How do you know if Eve still has your data? Now, obviously, the answer is like we're going to try and get Eve to prove in some way that she still has the data, or prove that she has like the answer to some computation, which is the data points. So solution 1 is you just ask Eve to send literally everything back. Now, this works If you send Eve all 1 million data points and she can send them all back later, that's fine. But it's a ton of sending stuff back and forth, and you might want to check like somewhat often. And like so that there's no scaling benefits here at all. And if you're just gonna need like all 1 million data points every time, then maybe you should just like keep them yourself. So this solution is like not so good yet. So solution 2 is we can just pick one data point and ask Eve to send it back. Now, this is much nicer, it's better, but Eve could easily throw away like, say like 100 out of the 1 million data points. And we would have like a 99.99% chance of like not catching Eve. And so Eve can get away with like losing a little bit of the data, which is like not a great property. So solution 3 is let's make a polynomial through all 1 million data points and then ask for the polynomial to be evaluated at one random point outside the original data. This works really well because, as we said before, different polynomials are different. So only if Eve actually goes through all 1 million data points will she end up at the same sort of like random point as us. So if she changes even a single point or forgets like a single point, it's really like she won't be able to trick us. Like she won't be able to give the same random point later. And this, like the theory of this is kind of like error correcting codes. If you're familiar with error correcting codes, if you send like a code over a noisy channel and some of the bits get like messed up, you can still, with error correction, you can fix like some small errors, and it's the same idea here. So ZK, the way like we use it is for proving that some computation was done correctly. And more or less, like we're going to want to encode our problem all the way down to a polynomial and then prove that this polynomial is correct by randomly checking it at a similar point. So we can even keep making the solution better. By one, we want to make it cheaper for like you to verify. We should also make it cheaper for Eve to generate the polynomial. And 3, if we can get the proof size to be really small, then that's nice also. So like if it's just a single field point, that's perfect. If it has to be a little bit more, that's fine too. Like maybe we check Eve at a couple field points just to be a little more safe. That's actually something we do at ZKsync. Nice. Now introduction to, or let me pause there and just see if the math example made sense. Now someone remembers the slides. All right, yes, I admit I've raised some slides. Isn't the problem statement the definition of DA? Yes. Oh yeah, Schwartz-Zippel is this, like Schwartz-Zippel is like the generalized version of the fact that like a degree n polynomial has at most n roots. That means like 2 different degree n polynomials intersect at most n places. Schwartz-Zippel's like the fancy way of saying that, but I don't know. In intro lessons, that's
Yes.
good.
I mean, like, I just appreciated the fact that you, without taking the name, you just explained all the concepts. That was beautiful.
Yeah. Yeah, you're right though. I should mention some of the names of buzzwords so that when people see them later, they like know what's happening.
Yeah, true. There's another question from Jenny.
Yes. How do polynomials dimensions scale with the size of data points? Is it 1-to-1? Yes, pretty much. So every like constraint you add to your circuit. So like if I want to prove 1 million additions, I pretty much need a degree 1 million polynomial if I prove it all at once. And a degree 1 million sounds huge, but our field size is still like to the 256, which is like much, much bigger. So yeah, it works out fine. Also, remember, only the prover needs to worry about the size or the degree of the polynomial. It's like mostly a pain for the prover, and the verifier usually has like a much simpler check to do. The computation for each degree is negligible. I mean, it is important for like, so if you want to like get the proving time as fast as possible. So at ZKsync, we prove like huge batches of data at once, and to reduce the proving time, there are certain tricks you can do to keep the degree size down. So one of them is having different circuits for different like specializations. So if you try to put a whole ZK rollup into one just mega big circuit, yeah, the degree would probably be too big. We split it up into like 12 or 13 different types of circuits, and each one's a little specialized. I'll get to those actually later in this lesson. And then the other one is lookup tables. I'm not going to talk too much about lookup tables today, but you can avoid increasing the degree a lot for like certain equations if you use lookup tables instead. What do you mean by a data point outside the polynomial? There are asymmetric polynomials. There won't be any points inside or outside. Okay, yeah, sorry, I probably didn't phrase that well, but what I mean is like, if my original data points are at 0, 1, x equals 0, x equals 1, x equals 2, I want to randomly check at like x equals 10 or something. I don't want to ask for one of the points that I've currently given. I want to ask for some point that's like just way out there. And that's kind of what gives us the nice properties. Like I said before, if you ask for a point that you kind of currently had, maybe the prover or Eve is like has that point, but not some of the others. If you ask for a point outside of the original domain, then the prover can only like figure it out if they actually do have all the data. What would be an approximate upper limit for the degree of a polynomial to be reasonably computable? In practice, almost every rollup is around like 2 to the 20, which is about 1 million degree polynomials. I've seen up to like 2 to the 24, and I think might be risk 0 is doing up to like 2 to the 27. But that's like 128, so like 100 million. So all the degrees are between 1 million and 1 billion, more or less, for these circuits. If it's much bigger than that, a lot of times like the bottleneck ends up being the amount of like RAM in your computer. And it's just like a lot of data to fit. It's better to break your problem down into small pieces and prove each of the small pieces than to try and do like one massive chunk of everything.
And just to be clear, risk 0 is doing the computation part off chain, right? Not on chain.
Yeah.
That's why they can go so much bigger. Okay, fine.
Mm-hmm. Well, it's one nice benefit of like rollups is that like only the verification needs to happen really on chain.
Yeah.
And
Yes.
so it's verifiable, but you get lots of good scaling. Okay, onwards. Where did I leave off? Yeah, so introduction to ZK snarks. So this is like, I guess the most common type of ZK proofs that you will see. And it stands for zero knowledge, succinct, non-interactive argument of knowledge. Succinct means that it's cheaper for the verifier than for the prover. So you don't have to do that much work to check these things. Non-interactive is a nice property. This comes from the fact that a lot of the like academic versions of these protocols, you have to go back and forth with like Eve and back and Eve and back. So like I said, you could check Eve at multiple points. And I could say, hey, I want to know the value at x equals 1 million, and at x equals 1,000,005, and at x equals 2 million. If you go back and forth 3 times, it works. Or you could just ask for all the points at once. And so non-interactive, it's like very useful because then the prover could just generate something once and send it once, and they don't have to like go back and forth with the verifier, which would be like much more difficult in practice to use. And then argument of knowledge is proving that they know something. Technically, it is an argument, not a proof, because we're using a little bit of probability here. So the chances of we could accidentally like mess up with probability, like the degree of the polynomial over the field size, which should be like very, very small. So we should like, this should work 99.9999% of the time with like a bunch of nines. So like security for all the proof systems is at least like 2 to the 128 bit or 128 bits of security, if you're familiar with like that terminology. Oh, also before we move on, snarks versus starks. Don't worry about it too much. In my opinion, stark should just count as a type of snark. There is some like nitty-gritty cryptographic definitions where like starks don't quite fit into the snark circle. They're like a Venn diagram, and there's like a little bit of starks that technically aren't snarks, but I think the distinction's super overrated and it's not worth like discussing. Cool. How can we make our solution better? Yeah, non-interactive, make a polynomial through all the points, ask for the polynomial to be evaluated. So we can agree to check at x equals 5 million, but then it's easy for Eve to cheat because she sort of knows where the check is going to happen. And so she can like manipulate the data or like compute things ahead of time because she knows what's coming. Instead, we should not let Eve pick the evaluation data point, but we also want it to be non-interactive. So we use a trick called Fiat-Shamir transformation. And the slide's too old. You don't need a trusted setup for Fiat-Shamir, but the idea is that you can use basically a hash function as a way of getting a random number. So if the hash function depends on the circuit and the data that just happened, Eve doesn't really have control over the output of the hash function, and so you can get good random Eve can generate fair random numbers on her own that she can't mess with. Cool. And then making the solution better. Yeah, I don't want to read the whole polynomial. I just want to check a few points. So there are these things called polynomial commitment schemes where I'll make Eve commit to the polynomial, and then before telling her like which points I want to reveal it at, and then later I know she's not like changing the answer in the background. If you think about like just trying to play a game of like heads or tails over the phone, how do you know whether like the other person's not just like like have they actually flipped the coin, or do they just tell you that you've like lost every time? And so a commitment scheme is a way of getting them to like commit to one answer, either heads or tails, and then you can pick, and then they can reveal it, and they can't change the answer since they've already committed to it. One more trick is a Merkle tree. A Merkle tree is just a like hash binary tree. So you start with the data in the bottom row, and at each layer, you're just hashing the leaves below it. And this way you get one hash at the top. And the Merkle tree is like very useful in many contexts, but it works well as a commitment scheme as well, because if I have all my data points at the bottom, I have the hash at the top, I can like reveal one of the leaves is in the tree with only like log n hashes, which is like nice scaling properties. Cool. Yeah, problem with the polynomial commitment. If I don't read the whole polynomial, how do I know it's a polynomial? In particular, you have to check if it's like low degree. This is like a little bit more of a detailed that, but anyway, this is how we get to things like fry, which is what's used in most Starks, is fast read element interactive oracle proofs of proximity. And the whole point is just to make sure the polynomial degree is low. But let's zoom in a little bit on how it works. So here we've got, I guess, 100 million columns each way. And rows must be close to, oh, I guess it's 1,000 by 1,000, I think. Some of these numbers are off, but it looks like it's supposed to be 1,000 rows, 1,000 columns. I don't know where I got this diagram from. And yeah, so the rows should all be at least like degree 1,000 polynomials, and the columns should also be degree 1,000 polynomials, and same with the diagonal. And so the point is that you can check that a lot of rows and columns are degree 1,000, and it avoids you having to check whether anything was like degree 1,000,000. So getting even better, there's further ideas like recursive snarks, where you can start with the problem, create a proof, and verify the proof. Or you can verify a proof that verifies the proof. You can verify a proof that verifies the proof that verifies. And so you can go in circles with this. And this can be nice for like several different ways. You can get like cool Mina style recursion where you like prove the entire history of the blockchain all at once. You can also just like, if you broke your problem down into several small problems, then you could prove that all of those sub-problems proofs passed it. That's what we do at ZKsync. So like I said, we have like 13 different types of circuits, but we don't want to post 13 proofs on chain. So we aggregate them recursively down into just one proof. All right, let's pause there again. Oh, no more questions. Okay.
I have a question.
Yes.
So, is there a difference between recursive snarks and recursive stocks? Like, how do I basically join two different proofs to make it one proof? Like, what is happening there?
Yeah, I would say recursive snarks and recursive starks are mostly the same idea. What you want to do is you want to write the verifier logic back in as like top level constraints. And this way, like the output of your first proof can be like used as data input to this other, to like a verifier proving circuit. And then you can go in circles as many times as you want.
Okay. Okay.
What would be an approximate upper limit of degree for a polynomial to be reasonably computable? Oh wait, I already answered that one. Yes.
Yes.
Okay. Cool. Continuing on then. So I call it buzzwords, but there's like actually interesting content. It's just like a lot of words that might be unfamiliar and are helpful to know. So how do we really get that polynomial? All of this has been kind of mathy and abstract, so let's bring it back to something that you might actually be able to program. So the original way that everyone turned their code into polynomials was using something called a rank 1 constraint system. This name comes from like logic theory mostly, but the idea is simple. Here we have a visual tree you can look at. The inputs are all the data at the bottom, x1, x1, x2, and 1. And there are intermediate values along the way, u, v, and y. And then there's a final output value, z. And so you can kind of read up the tree. U is going to be x1 times x1. Y is going to be like x1 plus 1. And so if you just keep putting things together up the tree, you get to the top. And once you have sort of your code in this form, then you can prove constraints about it, which is like you'll prove that U is actually equal to x1 times x1, and then you'll prove sort of like each step along the way. And so that's kind of, if you were wondering how you turn the code into a polynomial, it's through data structures like this. And also, yeah, there's only addition and multiplication here, but you can encode like a lot of logic, such as like a if statement can be like a selector times the first branch, and then plus 1 minus the selector times the second branch. And then, like, depending on whether the selector is 1 or 0, you'll either go to the left branch or the right branch, and that's it. So you can encode fancy things into this.
The thing that you just mentioned,
oh yeah,
sorry, the thing that you just mentioned about if statement, that was arithmetization, right?
Yes, yeah.
Okay.
Yeah, that's the term for this piece, is arithmetization. Fancy way of...
Then we, yes, sorry. Okay.
Go.
Yeah, I mean, and then we come on to R1Cs, like after arithmetization.
I guess yes. I tend to think of like everything up to like witness generation, like getting into concrete numbers is like part of arithmetization. It's all like the setup, sort of like you need to get towards the polynomial, and then you need to prove facts about the polynomial. And I in my head, I split like ZK into those two steps, and yeah, there's probably sub steps, but I don't worry too much about the distinction. But maybe I'm wrong. Or maybe I should worry more about like getting exact terminology precise. Anyways, here is a common one important thing that I've kind of glossed over until now, which is that we obviously have a prover and a verifier, but there's this missing piece called the setup. And so why do we need a setup of some kind? It's that the verifier needs to know like somewhat what's coming. So the verifier needs to kind of already know like the shape of the problem, or like the general like circuit we're trying to solve. And the way that they know that is through a setup algorithm that's run one time at the beginning. And you'll see there's a PK and VK on the screen. It stands for public key, or prover key, and verifier key. Sorry, it does not stand for public key. It's very confusing. Also, the prover key and verifier key, these are not like private things. I think it would be better named if they were just like prover parameter and verifier parameter, but it is what it is. Everyone calls it keys. And so anyways, you do a setup algorithm once, and then the prover gets some prover parameter, verifier gets a verifier parameter, and this helps the verifier, when they receive the proof later, make sure that this proof actually matches with the thing they were hoping was going to get proved. So when you look at the flow of like a circom circuit, you write your circom at the top, and going down the right branch, there's a setup which creates a proving key and a verifying key. And then on the left side, from your circuit, you also need to do witness calculation, which is like the circuit itself really just says like, I want to make sure that like x1 times x1 is equal to u in this example. But when we run it in real life, there's going to be numbers there. So it's going to be like 3 times 3 is equal to 9. And so the circom circuit just says x1 times x1 equals u. And the witness is saying x1 is equal to 3. And so u should be equal to 9. So running the witness input like values through the circuit is kind of what the prover does. And out of the prover comes the proof, and send it over to the verifier, and the verifier can use the proof and the verification key to check whether things are true or false. So a lot of moving parts, but hopefully already this is like all making sense and just super obvious that you should do all of these steps. So if it's making sense, I've done something good. So yeah, basic CIRCOM example, just to show a little code is, so you have your version at the top, and then a template is like a sort of block of code that you can reuse multiple times called multiplier 2. You have signals for inputs and outputs. A and B are inputs, C is an output. And then the next line, C less than double equal A times B is a constraint. And so that constrains the output C has to be equal to A times B. And then component main can just be a multiplier 2. So that's an example of like a little circuit. And then you can build up from there all the way to huge things like ZK rollups, which is fun. Here's like a little bit. I like this diagram a lot. I think it's from Dan Bonet originally on snarks versus starks versus bulletproofs. These are all like in theory, like academically how they're supposed to work. I'd say the proof sizes are very accurate. Like that's going to be the same in theory and practice. But what we found is that starks actually are very nice for the prover, and then snarks are very nice for the verifier. So what ZKsync does is we start with a stark proof, and then we recursively verify it through a snark proof. So like our big machine only has to do like can do the faster method, but then when it's time to verify on Ethereum, we want it to be cheap for Ethereum. So that's why we wrap it into a snark. And then bulletproofs are like a third kind that technically fall outside the realm because the verifier for a bulletproof is linear. So you haven't really saved the verifier extra time in theory. So not that many people actually use bulletproofs except the privacy teams. What is R in the diagram? I think R is like, I would guess it's like the circuit shape. I'm not quite sure. I didn't make this diagram either. I just find nice ZK diagrams on the internet. But mostly you shouldn't have to pass anything besides the proving key and the verifier key to the prover and verifier. I mean, R comes in the top and then it's like in every single picture in this diagram. So I don't know what its purpose is. Okay. Oh yeah, ZK Battleship is a fun example. If you just want to like play with a like, I don't know, when I'm learning something, I get annoyed that a lot of examples are either like super beginner or way too complicated. And I think ZK Battleship is a nice like in between where it's large enough to be interesting, but small enough that like, you know, it could have been like a very successful hackathon project or something. So if you want to like play with ZK and get your hands on it, it's a nice project to look at. Some more good resources. We're not done. I have a whole nother section on how ZKsync works, but just some good resources for now. Also, I can share these slides with you all afterwards. At Matter Labs, we have a big GitHub repo called Awesome Zero Knowledge Proofs that has like 100 really good resources. So you can always just dig through there for whichever topic that you want some good resource on. Vitalik's blog posts on Starks are very good. Each of them is only like maybe 2 or 3 pages to read. It is a little dense. It'll take you probably like 30 minutes to an hour for each of them. But Vitalik is like actually an excellent technical communicator. The ZK whiteboard sessions by ZK Hack, pretty much everything by ZK Hack. They run the ZK like conferences that you see. They host like a lot of the ZK podcast and many other events. It's a great organization. And then 0x Parks has some ZK classes on Circom and Halo too. And if you're just looking to program, then I recommend the 0x Park classes the most. If you want to know more about the math and stuff, then the other classes can be good. And I have a YouTube video on the Tornado Cache paper, which is fun. I'm a big Tornado Cache fan. So yes, look at that one too. Z Prize is another fun community thing to keep your eye on. Every year they put out like an open competition for people to try and make like breakthroughs or advances in ZK. And so anytime you kind of want to know like, hey, what are the researchers in the field like currently working on? You can go check out Z Prize. You can look at last year's like winners and stuff. They're another good group. All right, time to talk about how ZK rollups really work. So hopefully by now everyone understands ZK and has some intuition for it. But let's answer questions. To what other types of multi-party computation can you apply SK or ZK? So like ZK is already like a basic form of multi-party computation. Like I said, we try to make it non-interactive, but most of the protocols are designed with 2 parties in mind. And so the way I see it is actually like a sliding scale where digital signatures are like the simplest version. And then ZK is like more advanced and gets a lot more cool things. And then like full multi-party computation is like even beyond ZK, and these are like bigger concentric circles. Each one contains like the smaller one. Like there were a lot of things you could do just with digital signatures, and then ZK is like that on steroids, and then multi-party computation is like ZK on steroids. Cool. I think we're doing well on time too. So for a ZK rollup, what do we need to prove? So we want to be just as trustworthy as Ethereum, which means that we have to prove the state difference, but more or less like we just need to prove every computation that happens inside of our L2 needs to be proven so that the L1 can check that everything is being done correctly. So in practice, this means we need to prove all of the EVM opcodes. So everyone who calls a smart contract that does anything, we need to be able to prove adds, subtracts, multiplies, shifts, jumps, storage reads. We're going to need to prove memory and storage. So anytime we like load a smart contract or like store some value in memory, we need to prove that's being done correctly. We'll also need to prove all of our precompiles, EC recovery, catch-hack, SHA-256. And yeah, are we executing the correct code? So we need to prove that the bytecode that we're running on actually belongs to the smart contract that's being called. And we'll also prove events and L1 messages. These are like, just like an event is, or an L1 message is like an event that's sent from the L2 down to the L1. Events that just happen on the L2 and stay on the L2, like these are mostly similar to handle, but sometimes you want your message sent down to the L1. Cool. So that's pretty much it. And then we need a circuit for each of those. And ZKsync's current proof system is called Bujum. We upgraded to this about 3-4 months ago now. And I guess 4 months ago, it's April. And like as soon as we upgraded, we've had pretty much the cheapest proof system ever since then. Like this upgrade was awesome. Our new proof system is so good. And it's actually crazy that like we've come so far with ZK that like a lot of times we can be cheaper than optimistic rollups is like awesome. So anyways, we need on the left, we have the opcodes, and on the right is the circuit that proves that these things are being handled correctly. So for each of those opcodes, we have a circuit called the main VM circuit. This is like the biggest circuit that does most of the work. And the only thing that's going to be left out is some things that will get passed on to specialized circuits. But anyways, there's multiple cycles. Each cycle computes one opcode. And then, but stuff like storage read is very expensive versus like proving an addition is very straightforward. We've already seen that example. So we're going to want to not prove storage read right now, but we'll push it to another circuit that'll be specialized at handling storage reads and writes. So yeah, memory and storage will each get their own circuit called RAM permutation and storage application. Yes, so did Rahul have something to say?
No, good.
Okay. No, we're still going. Someone's typing now. I'll wait for the question. What data ZKsync needs to post on chain for verification? What's the trust assumption? That is an excellent question. So we so the data gets posted in like call data or blobs, but like what actually is contained in that data is, well, one, the actual proof itself, that needs to be sent. And then the other sort of half of it is we also need to send the like some of the witness data, so things that we're trying to prove. It's not enough to just have a proof. You need to know that it's like proving, like you need to know what data it's proving is like the new state. And so it's called like, yeah, the actual like difference. So sorry, not explaining this well. Let's do an example. I do one transaction to Rahul. My account balance goes down by 1 ETH and his goes up by 1 ETH. I will need to post on chain, or ZKsync will need to post on chain that both of our account balances have a difference. And then the proof will prove that the differences add up to like everything balances out and all the differences really correctly accounted for. Does that make sense?
You can tell them why ZKsync uses state diffs and why is it better than Polygon's full transaction that they post on chain.
Yeah. So why are state diffs better is that let's say like an Oracle has to do an update like ideally every single second. With Polygon, they have to pay full price every single time. So if they do that, if the block time's like a minute, then they have to pay like 60 times transaction fees at Polygon. Versus with ZKsync state diffs, there's just one big difference between like the first Oracle price and the last Oracle price. And will ZK prove everything in between was correct? But the Ethereum itself only needs to worry about like the start of the block and the end of the block. And so for Ethereum's perspective, there's only one state diff, so we only need to charge once. So that would be like a 60x cheaper application on ZKsync than on Polygon. Okay, so the other question was, what's the trust assumptions? So with ZK, unless there's like a cryptography bug, which in the early days like might happen, you can just like a proof will only pass if it was done correctly. And so as soon as the new proof comes in, you can be sure that the previous the new state update is valid. This is why like ZK makes for very nice bridging and like a bunch of other good properties, is that it's basically way better to trust the ZK proof than optimistic rollups where you don't really know when new data comes in, whether it's like correct or not. You have to wait a week for like a fraud proof to maybe come by. So that makes for like much worse
if the
bridging.
fraud proof is live on the chain.
Yeah, true. If someone even like makes fraud proof, or if you have fraud proofs.
If fraud proof even, yes.
I think Optimism says it's on testnet, maybe, but we'll see. If a transaction is super complex and produces a lot of state changes, wouldn't posting state diffs be more expensive? Theoretically, but like almost every transaction's just interacting with like one smart contract or just doing your balance. So like in practice, there's much more people who are like doing the same things repeatedly than there are people who do like 50 scattered things at once. But even with the 50 scattered things, like optimistic rollups still need to update like all 50 of those places and post it on chain. So it's not clear even then that like I think state diffs are pretty much always better. Like you're either saving data or it's the same amount of data.
Exactly. I mean, even in like super complex transactions, whatever, the number of state diffs would never exceed the number of transactions. And if someone is posting raw transactions on chain, which many ZK rollups are, then at our worst, we'll match their normal thing. We cannot go worse than them in data posting costs.
With how far things have come, what are the most pressing problem solutions you're focused on now? That's a great question, but let me get to that at the end of the slides. Because I do want to talk about the future, but let's go through what we have. Okay, so yeah, still precompiles on the left. They each get their own circuit. I can speed through it because you guys are fast learners. Are we executing the correct contract code? That's in the code decommitter. And then L1 events and L1 messages are so similar that we can put them in the same circuit log sorter. And then it's just the question of like, do we send it to the L1 or not? And all of ZKsync circuits together, if you want to see the full flow, we start them. It's a little hard to read maybe on the slide, but the main VM and the top right middle, that's the main circuit. And then the gray things are like the data that's sent in between. The white boxes are all the circuits. So yeah, main VM at the very top, and it goes down into like on the left side, code decommitment sorter, the code decommitter, catch SHA. It should be easy recover down there, and then RAM permutation. And on the right side, you have the log demuxer, just like splits up the data into the appropriate places. And then you have a storage sorter, storage application, events sorter, L1 message sorter, L1 message hasher. So it's kind of like a big, what's it called? I don't know, tree of stuff. So that from at the start, nothing's proved yet. And by the end, every single possible function has been proved. Cool. So current state of ZK. Here are ZK projects that you should maybe know. On scalability, I think ZKsync, Polygon, and Scroll are like all doing well. All good quality projects. There's some other good ones, but these are like just to name a couple. As far as privacy goes, Zcash and Monero are both like older projects, super cool. And then Aztec's coming out soon. Zcash and Monero are like their own L1 chains. Aztec is interesting because it's going to have smart contracts. There's other people trying to do private smart contracts also, like Aleo and Nomada. But I'd say these are like the most well-known. And then there's lots of cool ZK projects. I think too many people get caught up in just the privacy and scaling. But like the main point of a ZK proof is you're like proving something. And so there are lots of like interesting ideas just around the verifiability part. And you can check out projects like ZK P2P, ZK Email, and ZK Oracles. All of those are like very interesting things that aren't directly scalability or privacy. They're more just like, it's nice to verify things. Okay, we have a bunch of questions. I should answer questions first. How does Validium compare to ZK rollups? The only difference is where do you post the data? So full ZK rollups post all of their data to Ethereum, so Ethereum can verify everything. But the posting of like large amounts of data to Ethereum can be like the most expensive part a lot of times. And so with a Validium, you post all of your data to some data availability layer, and that could be Celestia, it could be like EigenDA, it could be like your own solution. But Validium versus ZK Rollup is just where do you post the data. So you lose a little bit of like security if you post the data elsewhere, because the like Ethereum is like super trustworthy, and then like wherever other place you're posting the data is probably like not quite as good as Ethereum, but could still be like very nice. I've heard statements that claim that EVM is not really designed to be proven, and some things are really difficult to prove. If true, which parts are those? I mean, looking back to this diagram, I'd say like at this point we've gotten good enough at ZK that like those sorts of concerns were like a big deal when we were trying to do ZK for the first time. Now it's much better. The hardest part of well, I would say the biggest difference between a lot of the ZK rollups and Ethereum is Ethereum like updates its global state tree after like every single transaction. And if you tried to prove that in a rollup, it would like, it's a ton of data. So really we just want to prove like the start of the block and the end of the block. And that's the only time we want to bother building the whole global state tree. So there's some like, they're mostly like technical differences that I think can either be like Ethereum will probably change to be more ZK friendly over time, and they're also not big roadblocks right now. So I don't think that's like too much for worry anymore.
I think they may be referring to that fact that things like SHA-256 are based on bit manipulation, while hashing algorithms that favor field arithmetic like Poseidon would have been easier to build on circuits instead of like HI.
That's a good point. But then we also have like lookup tables now, which make proving those like binary operations a lot better. So yeah, I'd say like this, the state of the art, like the cryptography researchers have like solved many of these problems and made it much better. Does ZKsync post all the data on Ethereum? Currently, yes. In Validium, how do you verify data on chain if data is not available on chain? Great. So, I mean, basically the answer is you aren't like, it's in Validium, it's not quite as good as posting all the data on chain. I think what Celestia is doing is they will actually have their own form of ZK proof that they have the data, and then Ethereum can verify a proof from Celestia that the data is on Celestia. So, no, go ahead, Rahul.
I mean, that's what like I was going to say, that this is also what Avail is doing, that you can post your data onto Avail or any other DA, and Avail will basically give you the proof that it has your data and it has the data intact. But what I wanted to like hear from you was that can you like would you like to talk about ZK Porter, because that is a solution for Validiums, I guess.
Yes. Yeah. So ZK Porter is very cool. It is I think we're calling it a volition, which is a combination of a full rollup with a Validium, and it really only works with state diffs. So this is actually, I think, the biggest reason to use state diffs. But how it's going to look long term is users will be able to choose whether they want their data stored on Ethereum or they're fine with some other DA layer. And so if they choose Ethereum, it'll be a little more expensive, but a little more secure. But if they choose to be on some other DA layer, then it'll be like much, much cheaper. And the cool part is because of state diffs and like ZKsync has been building from day one to be able to handle this, we'll be able to keep both the Ethereum accounts and the ZK Porter accounts on the same chain pretty much. So there's no like fragmentation. We don't have to like kick the cheaper users to like their own chain. We can actually kind of keep it all together in one like execution environment and prove all the diffs and just post the data different places. So it'll work like pretty seamlessly for users. This should be like really amazing for like if like transaction fees are like a big concern, maybe because like you don't have as much money and can't afford like very much, you can take the cheaper option. Or you could just choose to take the cheaper option most of the time, but then store like your most important things on Ethereum. That's kind of how I see it working, but it's going to be like really cool. Do you think I covered it well, Rahul?
Yes, that was perfect.
Nice.
I wish someone from Rahul and Porter were here, but okay.
I'm down to go toe to toe with anyone else in the ecosystem. I think we're actually building the best stuff.
I mean, every time I talk to them, all they have to say is that, hey, you're building a type 4. I mean, that's it. That's all they have.
Yeah, I get tired of some of the old arguments. It's like, anyways. Can ZK be deployed to obscure the value of some variables in a smart contract function on a network that is otherwise public and permissionless? So the way we use it is we are not trying to do any privacy at ZKsync. At least not for now. Like it's easy to turn a ZK proof from like mostly public to mostly private. And like the math is like 99.9% the same. And you just like add one extra step at the end. A lot of times you just like prove the hash of something instead of proving directly the thing. But the way we're building it is like we post all the state diff data down to Ethereum in the first place. So the data is already public. So generating like a private ZK proof doesn't like actually have privacy. You would also want to keep the data private. But theoretically, can you use ZK to like build private smart contracts? Yes, this is like what Aztec and a bunch of other teams are working on. The paper that kicked it all off is called, I forget the name of it now. The Alio people wrote this paper that basically showed everyone for the first time how you could do private smart contracts, and a lot of teams are, there've been like improvements since then. Privacy is cool. I'm a fan. I hope.
Yeah, I think you can write smart contracts with Neuer in the SDK ecosystem.
Yeah, Noir should make it easier for developers. What are your views on FHEVM? So yeah, fully homomorphic EVM I think is like super amazing. I think the Zama team is one of the strongest teams in the space. I also think you should always ask the question with homomorphic encryption of who are you actually encrypting to, like who has the encryption keys? Exactly. And the sad answer for a lot of these FHEVM projects that I've seen spinning up is that the validators have all of the keys. And so you as the end user don't actually control your own privacy. It's the validators on the network.
Nice. So with this last question on homomorphic encryption, we wrap up this session on ZK11 with Porter and Rahul from ZKsync. Thank you everyone for the engagement, the questions, and for showing up, obviously. And thank you especially to Porter and Rahul for being here and accepting our proposal to our invitation to come to the org and give us an upskilling workshop to all our members and community. We'll see you on the next one, and thank you for sticking around. Bye-bye.